Hello, my name is Bruno Gomes and I will present the work entitled Analysis of Thermal Radiation Models in the Presence of Different Levels of Turbulent Fluctuations. This work was developed by me, my colleague Guilherme Fraga, under the orientation of Professor Francis França. We are from the Mechanical Engineering Department of the Federal University of Rio Grande do Sul. As a brief introduction to the topic TRI, turbulence radiation interaction, is a complex phenomenon because it's a highly nonlinear coupling between fluctuations in radioactive intensity and fluctuations in temperature and medium composition. When we neglect these fluctuations, significant errors can occur between the calculated values and the actual values. The objective of this work is to test the accuracy of different WSDG models when subjected to the effects of turbulence. Reactive flow in a one-dimensional domain will be simulated in the presence of different levels of turbulent intensity to discover the variations of the errors according to those variations of intensity levels. For comparison purposes, the LBL model will be used as a benchmark. Now, I will talk about the theoretical basis of this work. First, when we talk about thermal radiation in the participating media, we can quote the radiative transfer equation, RTA. According to Modest, for a non-scattering condition, it's given as the equation shown here. Now, on line-by-line integration, LBL, this is a method that consists of solving the radiative spectral intensity along a path of each of the spectral positions. Then we get the value of the total intensity when we integrated the intensities for the whole spectrum. This is the weighted sum gray gases model, which consists of evaluating the analysis of different small j portions of the gas evaluated in the flow. According to Modest, the analysis of the intensity for each small portion of the gray gas can be described by the equation shown. The total gas intensity being given by the sum of the intensity of all j gray gases portions. Now, on TRI, as already mentioned above, it is the highly nonlinear coupling between fluctuations in temperature and composition of the medium, and fluctuation in radiative intensity. More generally speaking, TRI is the union of turbulent effects in a radiative flow. To bring the terms of the turbulent fluctuations, RTE time averaging is used, according to the first equation. The RTE has terms of absorption and emission. Through the OTFA, it is possible to simplify the terms related to the absorption. In order to describe the total average emission, a RTE model developed by Snegiev was used according to the second equation, where the term IB represents the total emission evaluated at the local temperature. Then, it's possible to neglect the last term of the right hand of the equation using the constant C, TRI true, equal to 0, then obtaining a more simplified equation as shown. Similarly, applying these same simplification steps to the WSGG model equation, we obtain the equation shown. The methodology of this work consists of solving the RTE shown previously in the presence and in the absence of TRI. To help solve the equation, the discrete ordinate method, DOM, was used. The equation will be solved for a one-dimensional domain, where the three different levels of turbulent intensity will be used. 0%, 40%, and 60%. 7 WSGG models were analyzed and compared with the LBL standard. They are Barba 2014, Cassol 2014, Doigon 2013, Johansson 2011, Keng-Won-Pon 2012 for fixed and variable mole fraction ratio coefficients, and in 2013. So the question arises, how to combine the effects of turbulence with the effects of radiation? The temperature variance was calculated by artificially introducing a temperature and turbulent intensity field, and so the temperature variation is inserted in the beta term of the RTE. The temperature field and the average concentration were created using equations used by Doigon 2030 in their study. Her fields come from equations for temperature profiles and molar concentration, whereby joining two of these form a specific case. Doigon uses 6 cases. In this work, we will focus on case 1 given by the displayed equations. It's worth mentioning that the ratio of CO2 to H2O is 1 to 2, that is why H2O is twice the CO2 value. Here are some results, but first, some information about them. To analyze the accuracy of the WSGG models, the radiative heat source and radiative heat flux were evaluated. The results presented refer to case 1, since it is already sufficient to understand the problem. This will be evaluated for the various WSGG models. The other 5 cases will be demonstrated for the WSGG model of Doigon 2030, since the cases were proposed in his work. Here we have a table that shows the percentages of the maximum and average difference between the LBL method and WSGG models. The values in the parentheses represents the average errors, while those without parentheses represents the maximum errors. The percentage errors are shown for the 7 WSGG models and the 3 different levels of turbulent intensity. Through the color scale, it's possible how accurate each model was compared to the LBL method. Here are some figures for the purpose of graphically demonstrating the results obtained for each of the WSGG models. Left being the radiative heat source and right being the radiative heat flux. Beside is the average percentage between the average errors. Here we have the Barber and Cassol models. Now here we have presented the models of Doigon and Johansson. And here the models of Keng-Won-Pon with fixed coefficients and variable coefficients. And finally the model of ENC. Here we have graphically demonstrated the remaining cases in the order to demonstrate that the formulation and models correspond in the current way. Here we have case 2, case 3, and case 4. Now, here we have case 5, case 6. All of these cases are just for Doigon WSGG model. Now, the conclusions of this work. There is no influence of the intensity of the turbulence on the accuracy of the WSGG models, although there is a subtle improvement in accuracy when the effects of TRI are increased. That is, even if the accuracy improves when the level of turbulent intensity increases, it's not yet a significant increase when related to the level increase. Regarding the comparison of WSGG models with the LBL method, the average errors percentage is approximately 5% for the source term and the radiative heat flux. The WSDG models that have coefficients for variable molar concentration ratios show less accuracy when compared to the fixed ratio coefficient models. As a conclusion of this work, Johansson WSDG model presents the highest accuracy among the analyzed models with an average of errors for the source term of 2.2% and 1.5% radiative flux. The WSDG model from Barber stands out since the model presents the best accuracy among the models that use coefficients for ratios of variable molar concentrations. Here some references used in the work. Thank you for your attention.